going to be the bulk of what we're going to do is the numerical solution, which always works, provided there is a solution. Okay, this is basically boils down to what is known as a root finding problem. And I'll explain what root finding is, and then we'll get to how to extend this idea to a 6 degree of 3 degrees first, the planar one, and then the 6 UR5. Okay, so root finding is the problem of computing x such that f of x, okay, so compute x such that f of x equal to 0, and x need not be a scalar, it can be a vector. By a vector, I mean it could be any number of equations. So here's an example. Okay, I'll give you a simple one-dimensional example because it's easy to visualize this. If I give you this quadratic equation and asked you to find the roots of the quadratic equation, we know that the solution to this is x equals 0. Oh no, 0 doesn't work. I think it's, is it 1, minus 1? I think minus 1 is 1. Right? And the other one, I think it's 2. So those are the solutions, minus 1 and 2. So you can check, you can put minus 1 and you get minus 1 square minus 1. So 2 minus 2 is 0, and then 2 you do, so it's 2 squared, 4 minus 2 minus 2, so it's 0. So those are the solutions. Okay, so how do you get this? Well, if you draw a plot of f of x versus x, that's going to be a curve. It will actually be a parabola. And then the solutions are sitting right here. This will be x equals 2, and this will be x equals minus 1. That's what is meant to be, that's what it means to be the roots of an equation, is where the curve meets the x-axis. Okay, now this is possible, that is, this visualization is possible for 1D, where f of x is, where x is the unknowns, right? That's what I mean by 1D, is that x. For 2D, you'll have x and y, and then you can plot f of x, y on the z-axis. But then if you go to 3D, 4D, it's just not possible to visualize. So we don't want to rely on a graphical method like this. We need something more powerful than that. So there is a function called fsolve, which can be used for root finding. And that's what we're going to use. X squared minus x minus 2, I put it in a function. When using fsolve, it turns out that it is in a package called SciPy optimize. So I import fsolve, which is one of the functions inside SciPy optimize. First, I just make a plot of the function, just like I drew it there. So you can look at the plot. But then I also solve for the root by using fsolve, providing the function. And then I provide something else. This is actually an initial guess. So if you, it is a guess. I'll talk about that in just a bit. So let's just run this. It'll make a plot of the function. Okay, so that's the plot, minus 1 and 2. And then you can see it actually gave me the root. It's 2. So we know that root is 2 and minus 1. Okay, so now here's the thing about the guess. fsolve will only give you one root. Even though there are 2 roots, you can only provide solutions to one root. That's how fsolve works. If you want to find the other root, you need to pretty much try giving it another guess. So let's try 0. So the plot, and then it gave you the other root, minus 1. So if you want to use fsolve to figure out the roots, you have to keep giving it initial guess and seeing what it produces. Now, there might be a case where it tells you that there's no root. It'll try, but it'll fail. Or it could happen that, in this case, multiple roots. You could try number of guesses till you start getting the same roots, and then you know the number of roots. Do the same problem, the inverse kinematics of this manipulator, using fsolve. Okay. So I wrote these equations. The only change you need to make in order for this to work is that you just move this around. So just say that this should be minus 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 equals 0 0 0. So this is f1. The x here is theta 1, theta 2, theta 3. So f of x is f1x, f2x, f3x equal to, well, 0 0 0. And note that the thing you are interested in solving here is x, which will contain theta 1, theta 2, theta 3. What's given is these things are given, the lengths are given. What is not given is the angles. So C1 is cosine theta 1, S1 is sine theta 1, C1 2 is cosine theta 1 plus theta 2, and so on, right? Okay, so that's all we need to do is program that f of x in that function. Remember that function I showed you for the root finding, and then it'll give us a solution. So I'm going to start off from the, so earlier in the previous lecture, we had talked about inverse kinematics, and I'm just going to start off with this one. It's much faster if I program from here. Let's call it inverse kinematics. And this file will obviously run. So let's rename this. Okay, so this is the file. This was a program I wrote down last time, which did the inverse kinematics analytically. So yeah, so it did this inverse. If you look at the function, it actually called inverse kinematics analytic, which I'll open and I'll actually modify it. So it used this function where it was really lots of things we need to do because we were inverting cosine, sines, checking, and so on. So I'm going to just modify this. Okay, I'm going to call this just inverse kinematics. And then let's go here and then call import inverse kinematics, and then call this function inverse kinematics. Okay, so we want the same xref, yref, theta ref. However, what we need here is we need an initial guess. So let's make some guess. 0.5, 0.5, 0.5, say. Okay, and then the inverse kinematics, we're using SciPy optimize. So what we need to do here is essentially take this part, and then use it here. Output would be Q. We'll call this function inverse kinematics. Okay, there's the initial guess, which is Q0. And then we need to pass this parameters because we need to tell it where exactly we need it to land. So there's a way to do that. I think it is args equals. Okay, everything else remains same. So provided I code this right, it's going to give me the Q, and everything else will proceed as we did it earlier. So let's write this function. Okay, so wrote that this function should just be providing it with this thing, this whole thing, f1, f2, f3, and that should be the return argument. That will be xc, the end effector position minus xref, y position minus yref, and then this sum of the angles. So let's program that. Okay, here it is. Save this. So I don't think I need any of this. but I do need to unpack this. So Q is the first argument, the parameters is the second one. Okay, so now what I'm going to do is I'm just going to see what I need to return. Let's say I'm going to call it xc minus xref, ye minus yref, and theta minus theta ref. Okay, I need to fill in the blanks. I have xref, yref, theta. I just have to get x, e, y, theta. Now it turns out that I've done this work. I don't have to repeat it. If I go to forward kinematics, it actually takes in q and then returns the solution, and the solution has this thing E, and this E happens to be the end effector position. So that's been already done by me, so I don't need to really worry about doing the inverse kinematic manually. So I just need to call this forward kinematics function. So let's go here and then call it. So sol equals forward kinematics, and the input should be Q. And then I said that would have sol.e. Let me unpack it as in E. And then I want to call xc to be the first one, and then ye to be the second one, because we have xyz is the xyz position of the end effector. Now I'm only left with theta. Okay, so how do I get theta? So if you look at the H homogeneous matrix, quite a bit of code. So the homogeneous matrix, actually the global one, this homogeneous matrix holds the end effector position, but also holds the angle. So the way this H is, in fact, it would be the third one. Third one, because that's the orientation of the last link. It will be something like this: R 03, O 03, O 03, 0, 0, 0, 1, right? And this R 03 will be something like cosine theta 1 plus theta 2 plus theta 3 minus sine, same thing, 0. Lost it. And then there'll be oh, just need to copy this. Okay, sine, and then there'll be cosine. 0, 0, 1. Okay, so this is how it will be. The output, I'm just going to comment it out, but this is just to explain. Now I need to compute, I need theta 1 plus theta 2, theta 3. That should be the third one. So I can get theta, which is arc np dot arc cosine arc cosine of robot 3 dot h global, and the element I'm looking for is since this is sitting here, it's going to be the 0, 0 element. So 0, yeah, and then I need to, so once I compute theta, I need to pass it back. So let's pass it here. All I need to say is theta equals theta. Now it's available for the inverse kinematics. So here, this sol has theta. And then that theta, so now I've completed the f of x. And then if everything works fine, when I run this, it should give me the solution, which will then go to forward kinematics, which will then do the animation. Okay, let's see if it works. Oh, it's the forward kinematics, my bad. Okay. Oh, yeah, robot.body. My bad. I should just follow this format. Okay. Okay, that's one solution. Remember, there are two solutions. So one you can try the other one. I'm just going to guess that some different initial guess will give me the other one. Let's see if it does give me the other one. Yeah, that's the other one.